Welcome to this problem walkthrough. Today, we'll be solving LeetCode number 2050, Parallel Courses 3. This problem challenges us to calculate the minimum time required to complete all courses, taking into account prerequisites and individual course durations. Let's dive into the details and break it down step by step. In this problem, you are tasked with determining the minimum time required to complete a series of courses. The courses are numbered from 1 to n, and you're given a list of prerequisite relationships between them. Each relationship specifies that one course must be completed before another can begin. Additionally, each course has a specific duration, given in the time array, which indicates how many months it takes to finish that course. The goal is to calculate the shortest possible time to finish all the courses while respecting these prerequisites. You are allowed to work on multiple courses simultaneously, provided their prerequisites have been completed. Once a course starts, it must be completed without interruption, and the time taken for one course does not interfere with others running in parallel. The output for this problem is a single integer representing the minimum number of months required to complete all the courses. For example, consider a scenario where there are 3 courses, with 2 prerequisite relationships. Course 1 and Course 2 must both be completed before Course 3 can begin. The respective durations for these courses are 3 months, 2 months, and 5 months. The objective is to determine how long it will take to complete all 3 courses while following the prerequisites. In this example, courses 1 and 2 can be taken in parallel because they have no dependencies. Since Course 1 takes 3 months and Course 2 takes 2 months, the total time for these prerequisites is the maximum of the 2 durations, which is 3 months. Once the prerequisites are completed, Course 3 takes an additional 5 months to finish. Therefore, the total time to complete all the courses is 3 months for the prerequisites plus 5 months for Course 3, resulting in 8 months. Now let's look at another example with 5 courses. Here, Course 5 depends on Courses 1, 2, 3, and 4, while Course 4 itself depends on Course 3. The durations are 1, 2, 3, 4, and 5 months respectively. Courses 1, 2, and 3 can be completed in parallel, so their total prerequisite time is the maximum of their durations, which is 3 months. Course 4 can only begin after Course 3 and takes an additional 4 months, making the total time for Course 4 equal to 7 months. Finally, Course 5 can only begin after all its prerequisites are completed, which takes 7 months. Adding the 5 months required for Course 5 brings the total time to 12 months. For a simpler case, if there is only one course with no prerequisites, the total time required is simply the duration of that course. For example, if the single course takes 5 months, the output is 5. To summarize, the problem constraints ensure that the input forms a directed acyclic graph, meaning there are no circular dependencies. The number of courses ranges from 1 to 500, durations can go up to 10,000 months, and the relationships provided will always be valid. Your task is to leverage these constraints to efficiently compute the minimum time needed to finish all courses. To solve the problem of determining the minimum time required to complete all courses, we need to consider the constraints of prerequisites and the individual durations for each course. This naturally translates to analyzing a directed acyclic graph, or DAG, where nodes represent courses and edges represent prerequisites. One potential approach is brute force, where we simulate all possible orders of course completion while ensuring prerequisites are respected. This can be implemented through backtracking or recursion to explore all valid course orders. However, the factorial growth of this method, with a time complexity of O(n), makes it impractical for larger inputs. Another approach leverages topological sorting combined with a breadth-first search, or BFS. By processing courses in a topological order, we can calculate the earliest time each course can be completed, using the maximum time among its prerequisites. This method significantly improves efficiency, with a complexity of O(n) plus E, where n is the number of courses and E is the number of prerequisites. While effective, it requires careful management of dependencies to ensure correctness. Next, we consider an alternative strategy that builds on topological sorting but incorporates dynamic programming, or DP. Here, topological sorting is again used to determine the order of processing courses. However, instead of propagating completion times using BFS, we use a DP approach to calculate the minimum time for each course. This is achieved by iteratively adding the course's duration to the maximum completion time of its prerequisites. With a complexity of O(n plus e), this approach mirrors the efficiency of the BFS method but offers a conceptually cleaner implementation. By leveraging the properties of topological sorting in DP, we can ensure correctness while avoiding the need for additional bookkeeping. The chosen strategy is therefore topological sorting combined with DP, as it aligns perfectly with the problem structure. Key observations include the DAG representation, where edges enforce prerequisite order, and the fact that course times depend on the longest prerequisite chain plus the course's own duration. The topological sorting plus DP approach stands out for its balance of clarity and efficiency. By combining these techniques, we achieve a solution that is both easy to implement and debug, while maintaining optimal performance. Although BFS offers a comparable complexity, it may require additional effort to propagate states effectively. On the other hand, brute force approaches are computationally infeasible due to their exponential complexity. This strategy assumes the input graph is a valid DAG, which is guaranteed by the problem constraints, and operates within acceptable memory limits of O(n plus e), even for larger inputs. In conclusion, this method is well suited to the problem's requirements, offering a scalable and optimal solution for determining the minimum time needed to complete all courses in a parallelized setup. By leveraging the DAG structure, topological order, and dynamic programming, we efficiently account for all dependencies and durations, ensuring correctness and performance. To solve the problem Parallel Courses 3, we need to determine the minimum time required to complete all courses in a directed acyclic graph, or DAG. Each course is represented as a node, and the prerequisites are represented as directed edges. This means if course B depends on course A, there's a directed edge from A to B. We start by representing the problem using a graph. The input consists of n courses, a list of prerequisites, and an array time where each time, I, specifies how long it takes to complete course I. We use an adjacency list to represent the graph efficiently, as it allows us to store all the neighbors of a node. Additionally, we initialize an in_degree array to track the number of prerequisites for each course. This helps us determine which courses can be taken immediately. Next, we populate the adjacency list and the in_degree array by iterating through the prerequisites. For each pair, A, B, we add B to the adjacency list of A and increment the in_degree of B, reflecting that it has one more prerequisite to fulfill before it can be taken. Now that we've represented the graph, the next step is to perform a topological sort using Kahn's algorithm. Topological sorting is critical because it ensures that we process all prerequisites of a course before processing the course itself. We start by identifying all courses with no prerequisites, which are nodes with an in_degree of 0. These courses are added to a queue, as they are ready to be taken immediately. From there, we compute the minimum time required for each course. To do this, we maintain an array called min_time, where each element tracks the earliest time a course can be completed. For courses with no prerequisites, we initialize their min_time to their respective time values, since they can be started right away. While the queue is not empty, we dequeue a course, and for each of its dependent courses, we update the min_time for the dependent course. The update ensures that the dependent course starts only after all its prerequisites are completed. Specifically, we set min_time, next, to the maximum of its current value and min_time, cur, plus time, next. Finally, we decrement the in_degree of the dependent course. If its in_degree becomes 0, it means all its prerequisites are satisfied, and we enqueue it for processing. The algorithm works effectively due to a few key insights. First, topological sorting ensures that we process each course only after its prerequisites are processed. This guarantees correctness in the order of execution. Second, the dynamic update of the min_time array allows us to account for all incoming dependencies. By taking the maximum of the current and newly calculated values, we ensure that a course starts at the earliest possible time after its prerequisites are completed. This approach implicitly performs a critical path analysis, as the longest path in the DAG determines the minimum time required to complete all courses. To implement this efficiently, we use specific data structures. The adjacency list represents the DAG using O, V plus E, space, where V is the number of courses and E is the number of prerequisites. A queue supports the topological ordering, while the in_degree array tracks the prerequisites for each course. Finally, the min_time array stores the earliest completion time for each course. The algorithm runs in O(V+E) time, which covers both graph construction and the topological sorting process. Space usage is also O(V+E), making the solution scalable for large inputs. When applying this algorithm, it's important to consider edge cases to ensure robustness. If there are no prerequisites, all courses can be taken independently, and the result is simply the maximum value in the time array. For a single course with prerequisites, the algorithm ensures that the course starts only after all its dependencies are completed. Since the problem guarantees a directed acyclic graph, cyclic dependencies are not a concern, so we don't need additional checks for cycles. Finally, in cases where the graph is disconnected, the algorithm processes each connected component independently, ensuring that the solution is correct regardless of the structure of the input. These considerations make the algorithm both efficient and reliable for solving the problem. To solve the problem, we start by importing the necessary modules from the Python collections library. The deque is used for efficient queue operations, and defaultDict helps us build an adjacency list for the graph. Inside the minimum time function, the first step is to construct the graph and calculate the indegrees of each course. The graph dictionary maps each course to its dependent courses, while the in_degree list keeps track of how many prerequisites each course has. We populate these structures by iterating over the given relations, which represent prerequisite relationships. For each dependency pair, we add an edge in the graph and increment the indegree for the dependent course. Next, we initialize a queue to store all courses with an indegree of 0, meaning they can be taken immediately since they have no prerequisites. Simultaneously, we create the min_time array to track the minimum time required to complete each course. For courses with 0 indegree, we set their initial completion time to the time it takes to complete just that course. Then, we enqueue these courses to begin the topological sorting process. Finally, we enter the topological sorting loop, where we process courses in the queue one by one. In this loop, we dequeue a course and examine its neighbors in the graph. For each dependent course, we calculate the minimum time required to complete it by taking the maximum of its current time and the time to complete the current course plus the time for the dependent course itself. This ensures that we account for any prerequisite delays while determining the total time required. Once we update the time for a neighbor, we decrement its indegree, as we've effectively processed one of its prerequisites. If the indegree of a neighbor becomes 0, it means all its prerequisites have been satisfied, so we add it to the queue to process in subsequent iterations. Finally, after processing all courses, the min_time array contains the minimum time required to complete each course. To determine the overall answer, we simply return the maximum value in the min_time array, as it represents the total time required to complete all courses when taking dependencies into account. Here, we start by defining the minimum time method, which takes the number of courses n, a list of prerequisite relationships relations, and an array time representing the time required to complete each course. The first step is to build the graph and calculate the indegrees of each node. We use an adjacency list to represent the graph, where each course points to the courses that depend on it. The indegree array keeps track of how many prerequisites each course has. For each relationship in the relations array, we decrement the course indices by 1 to make them 0-based, then add the dependent course to the graph and increment its indegree. Next, we initialize a queue to hold all the courses with 0 indegree, as these can be started immediately. We also create a min_time array to track the minimum time required to complete each course. If a course has no prerequisites, we add it to the queue and set its completion time and min time to the value from the time array, since it can be completed independently. Now, we perform topological sorting while calculating the time required to finish each course. As long as the queue is not empty, we process one course at a time by pulling it from the queue. For each of its neighbors, we update the min time for the neighbor to ensure it reflects the maximum time needed so far to complete all prerequisites and the course itself. This is done using the formula math.max, min_time, neighbor, min_time, cur, plus time, neighbor. Then, we decrement the indegree of the neighbor. If the indegree of a neighbor becomes 0, it means all its prerequisites are completed, so we add it to the queue. Finally, after processing all the courses, we determine the maximum value in the mintime array, which represents the total time required to complete all courses. This value is returned as the result of the function. This approach ensures that we account for the dependencies while calculating the overall course completion time efficiently. To solve this problem, we'll start with a simple example involving two courses. The input specifies that we have two courses, where course 1 depends on course 0. The time required to complete each course is given as 3 for course 0 and 2 for course 1. First, we build a directed graph to represent the dependencies. In this graph, course 0 points to course 1, indicating that course 1 relies on course 0. Alongside the graph, we calculate the indegrees for each course. The indegree array shows that course 0 has no prerequisites, while course 1 has one prerequisite. Next, we initialize the processing queue with all courses that have an indegree of 0, which in this case is just course 0. We also set up a minimum time array, starting with the time to complete course 0 as 3 and initializing the time for course 1 as 0 since we haven't processed it yet. The next step involves performing a topological sort while calculating the time required to complete all courses. First, we process course 0 by removing it from the queue. Since course 0 has a neighbor, course 1, we update the time for course 1 using the formula max, current time, time for course 0 plus the time to complete course 1. This gives us a value of 5 for course 1. We then decrease the indegree of course 1 by 1, making it 0, and add it to the queue. Now, we process course 1, which has no neighbors, so the queue becomes empty. At the end of the topological sort, the minimum time array contains the values 3 for course 0 and 5 for course 1. The final step is to return the maximum value from the minimum time array, which is 5. This represents the total time required to complete all courses. Now, let's consider an example with multiple dependencies. In this case, we have 4 courses, where course 1 depends on course 0, course 2 depends on course 1, and course 3 depends on course 2. The time required for each course is 1, 2, 3, and 4 respectively. We start by building the graph and indegree array. The graph shows the chain of dependencies, with course 0 pointing to course 1 to course 2, and course 2 to course 3. The indegree array indicates that course 0 has no prerequisites, while the other courses each have one prerequisite. We then initialize the queue with course 0, since it has an indegree of 0. The minimum time array is initialized with the time for course 0 as 1, and the times for the other courses set to 0. Next, we perform the topological sort while calculating the time required for all courses. Starting with course 0, we remove it from the queue and process its neighbor, course 1. The time for course 1 is updated to 3, which is the maximum of its current time and the sum of the time for course 0 and the time to complete course 1. We then decrease the indegree of course 1 to 0 and add it to the queue. Similarly, we process course 1, updating the time for course 2 to 6 and adding course 2 to the queue. For course 2, we calculate the time for course 3 as 10 and add course 3 to the queue. Finally, we process course 3, which has no neighbors, leaving the queue empty. The minimum time array is updated to reflect the times for each course as 1, 3, 6, and 10. The maximum value, 10, represents the total time to complete all courses. In this example, we have 3 courses, but no dependencies between them. The input specifies that the time required to complete each course is 4, 2, and 6 respectively. Since there are no dependencies, the graph is empty, and all courses have an indegree of 0. We initialize the queue with all 3 courses, as they can be processed independently. The minimum time array is set to the given times for each course, 4, 2, and 6. As we process the courses, we observe that none of them have neighbors, meaning no updates to the minimum time array are needed. We process course 0, then course 1, and finally course 2, removing each from the queue one by one. The minimum time array remains unchanged as 4, 2, and 6. The maximum value in this array, 6, represents the total time required to complete all courses. Since the courses are independent, this is simply the time required for the longest course. To analyze the time complexity of the solution, we break it into several key steps. First, we need to build the graph and calculate the indegrees for each course. This involves iterating over the relations list, which has a size of m, and populating the graph while computing indegrees. This step takes time. Next, we initialize the queue by iterating over all n courses to identify those with an in degree of 0, which takes n time. Then, we perform topological sorting while calculating the minimum completion times. Here, each course is processed exactly once, and for every course, we traverse its outgoing edges. Since the total number of edges in the graph is m, this traversal takes time. Additionally, during this traversal, we update the min_time array and decrease the in degree of neighboring nodes, which are constant time operations. Finally, once all courses are processed, we find the maximum value in the min_time array to determine the total time required for all courses, which takes n time. When we combine these steps, the total time complexity becomes m for building the graph and calculating in degrees, n for initializing the queue, m for traversing all edges, and n for finding the maximum time. Adding these together, the overall time complexity is n plus m, where n is the number of courses and m is the number of prerequisites. Now, considering the space complexity, the graph is stored as an adjacency list, which requires m space to store all edges in the worst case. We also use an in_degree array, which has a size of n, taking n space. These components contribute to the overall space usage. Additionally, the queue used during topological sorting can hold up to n courses in the worst case, which requires n space. Alongside this, we maintain a min_time array to track the minimum completion time for each course, and this array also has a size of n, taking n space. When we add up all these components, the adjacency list for the graph, the in-degree array, the queue, and the min_time array, the total space complexity is n plus m. This efficient use of space ensures that the algorithm can handle large inputs without exceeding memory constraints. Comparing this approach to brute force or naive methods highlights its efficiency. A naive approach might involve recursively calculating the minimum time for each course by iterating over all its prerequisites. However, this can lead to exponential time complexity due to repeated calculations for overlapping subproblems. In contrast, the current solution uses topological sorting combined with dynamic programming to avoid redundant computations, ensuring a time complexity of n plus m. This efficiency is possible because topological sorting processes each course only after all its prerequisites are complete, avoiding unnecessary recomputation and ensuring a single pass over the graph. In the best case, when there are no prerequisites, the algorithm processes each course in n time. In the worst case, for a fully connected directed acyclic graph, the algorithm processes all n courses and m edges, leading to n plus m time complexity. The mathematical basis for this efficiency lies in how the algorithm processes the graph. Each course is processed exactly once, and each edge is traversed exactly once. This means the total work done is proportional to the number of nodes, n, and edges, m, which leads to the n plus m time complexity. Similarly, the space usage is determined by the adjacency list, which requires m space to store all edges, and the arrays used for in degrees and minimum times, which require n space. Together, this results in an overall space complexity of n plus m. This is a standard result for graph traversal algorithms like breadth-first search, ensuring both time and space efficiency for this problem. One of the most common mistakes in this problem is failing to handle cycles in the graph. While the problem guarantees a directed acyclic graph, it's still good practice to validate the graph structure explicitly. If cycles exist, they can lead to infinite loops or incorrect results during topological sorting. A good way to address this is by using a visited set or implementing Kahn's algorithm, which ensures the graph is acyclic as you process it. Another issue often arises with incorrect topological sort implementations. For instance, forgetting to decrement the in-degree of nodes properly or neglecting to process all nodes with zero in-degree can lead to an incorrect course order or missed dependencies. To fix this, you can use a queue or stack to systematically process all nodes with zero in-degree while ensuring every prerequisite is accounted for. Finally, overlooking multiple longest paths is another frequent pitfall. Some solutions mistakenly assume that only one path contributes to the course completion time, but in reality, multiple prerequisite paths might need to be considered simultaneously. To handle this, dynamic programming can be used to compute the maximum time required for each course by aggregating the times from all prerequisite paths. Another related challenge is misunderstanding the problem statement. For instance, some might confuse whether the course duration includes the time for prerequisites or is an additional duration after prerequisites are completed. This misinterpretation can lead to underestimating the solution. To avoid this, it's essential to carefully read the problem statement, paying close attention to how course times are defined. Inefficient graph representation is another common issue. Using nested loops to find prerequisites, instead of leveraging adjacency lists or matrices, can make the solution highly inefficient, especially for larger inputs. The best practice here is to use an adjacency list, as it allows for efficient edge traversal and better management of dependencies. This problem provides an excellent opportunity to demonstrate your understanding of directed acyclic graphs, or DAGs, which are a cornerstone of graph theory. You should be comfortable explaining topological sorting and its various applications, as these are likely to come up in interviews. Additionally, dynamic programming is often combined with graph algorithms to solve problems like finding the longest paths in a DAG, so it's important to understand this interplay. Be prepared to tackle edge cases, too. For example, scenarios with no prerequisites, only one course, or chains of dependencies that require sequential completion are all possibilities you might encounter. Lastly, interviewers may ask you to discuss optimization trade-offs. For instance, you might compare Kahn's algorithm to depth-first search for topological sorting, explaining the advantages and drawbacks of each approach in terms of scalability and implementation complexity. There are several related problems on LeetCode that can help you deepen your understanding of these concepts. For example, LeetCode number 207, Course Schedule, focuses on detecting whether it's possible to complete all courses by checking for cycles in the graph. LeetCode number 210, Course Schedule 2, builds on this by requiring you to return the course order based on topological sorting. LeetCode number 310, Minimum Height Trees, shifts the focus to tree-based graph problems but still incorporates topological insights. Finally, LeetCode number 329, Longest Increasing Path in a Matrix, is a great example of applying dynamic programming to graph problems, as it involves finding the longest path in a matrix represented as a graph. Practicing these problems will solidify your understanding of key techniques like cycle detection, topological sorting, and dynamic programming in graph-based scenarios. There are also alternative approaches to solving this problem, each with its own advantages and trade-offs. One option is using dynamic programming with depth-first search. Here, you calculate the maximum time for each course through DFS while storing the results in a memoization table to avoid redundant computations. This method is relatively easy to implement, though deep recursion can become an issue if not optimized. Another approach involves Kahn's algorithm, but with level tracking. As you perform topological sorting, you simultaneously track the maximum time needed to complete each course as prerequisites are resolved. This strategy is more iterative and scalable for larger graphs, but it requires careful management of in-degree values. Lastly, you could use an approach inspired by the Bellman-Ford algorithm. In this method, the problem is treated as finding the longest path in a DAG, where you iteratively relax edges to compute the maximum times. While effective for edge-based graph representations, this approach may involve additional complexity in managing course durations. Each of these techniques offers unique insights into balancing efficiency and clarity in your solution design. Great job on completing the walkthrough of LeetCode number 2050, Parallel Courses 3. We explored a topological sort and dynamic programming approach to solve the problem efficiently. I hope you found this solution helpful and learned some new techniques for tackling dependency-related problems. Don't forget to like and subscribe for more tutorials, and happy coding! That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!